Assalamu alaikum. My name is المفارجه. Today, me and my friend will be discussing our project that is talking about detecting myocardial infarction using ECG signals and machine learning techniques. Our goal from this project is to use simple methods that is still usable and useful in the medical field. First, let's start talking about problems and objectives. I will start with the problems. Myocardial infarction is one of the leading causes of death around the world. ECG is low-cost, non-invasive diagnostic tools that are used in many hospitals nowadays. However, ECG signals are often noisy and vary between patients, which makes the automatic detection difficult. Therefore, our objective from this project is to use understandable machine learning techniques to identify myocardial infarction in ECG signals. We took our databases from Physionet. As you can see, we use 4 databases. First one was the BTB diagnostic ECG. This was our main data set for training and testing because it contained records for healthy and myocardial infarction patients. Second one was MIT-PIH arrhythmia, was used for visual validation of ECG waveforms. Third one, ECG ID, helped us to demonstrate noise and interpatient variability. The last one was the European STT database, was used for understanding the ST segments and T wave change related to the myocardial infarction. Okay, this code shows how we tested the data sets, and we looped through each database folder, displayed the path, number of files, and sample file names. Let's start talking about it line after line. OS is a library that allows Python to interact with the operating system. These lines store the main folder of data sets that are saved in the device. This list contains the name of all ECG data. This is the loop that runs once for each data set. This combines the main path with the data sets. Gets all files inside the dataset folder, and this for the sorted one is for arrangement. And now for printing, we have the printing functions. First, print the dataset name, then print the dataset path. After that, print the total number of files, and lastly, print a sample of files. This step is important because it confirms that all ECG databases are correctly loaded, and it helps detecting missing files early, and it provides an overview of dataset size and structure. Methods overview. This slide summarizes the overall pipeline diagram of our systems. We start by considering the raw ECG signals, then applying some pre-processing steps to them. After that, we extract time domain features and apply machine learning classifications, and finally we evaluate the model performance. During pre-processing, we selected the lead 2 because it's commonly used in clinical ECG monitoring. ECG signals were segmented to 10-second windows. Then we applied Z-score normalization to standardize the signals and reduce amplitude variations. So normalization had the objective طبعا for improving accuracy and reducing the error percentage. As we all know, some medical data sets are often imbalanced. So we used class balancing through downsampling to reduce bias toward the majority classes. Of course, we mentioned furthermore information in our report. As you can see here, this is an example of signal before and after filtering and noise reduction during pre-processing. ECG loading and normalization. This code shows how we loaded and normalized the ECG signals. Fs represents the sampling frequency of the signal. This opens the ECG data file, and this line reads all data from the file into the array. This array rows contains the interleaved ECG signal values. This corresponds to the lead 2. The array T represents the time axis of the ECG signal. Then we normalize the signal by dividing it to the maximum absolute value. After that, plotting a short segment makes the waveform easier to visualize. This step ensures that the ECG signals are correctly loaded and converts raw data into usable signals, and for sure, normalization improves the feature extraction and model performance, and the visualization helps us to verify signal quality before further processing. Okay, we extracted the time domain features from each ECG segment. These parameters include mean, standard deviation, RMS, that means root mean square, peak-to-peak amplitude, skewness, and kurtosis. طبعا each of this parameter represents something. So now we will start talking about that. First, the mean represents the average signal level. Standard deviation represents signal variability. RMS represents signal energy and magnitude. Peak to peak represents the amplitude range, and the skewness represent the waveform asymmetry, and finally the kurtosis represent the peakedness and flatness. The reason of choosing these features, they are simple and computationally efficient and easy to understand from the biomedical point of view. Code of feature extraction. These functions calculate the time domain features for every ECG segment. Each of these features represent a particular characteristic from the ECG waveform. First, the mean of the signal computes the average value of the ECG segments. Then the standard deviation, it's measure how much the ECG signals varies around the mean. Then the RMS, root mean square. First, the signal is squared to make all values positive. Then the mean of the squared signal is calculated. Peak to peak, we have difference between the maximum value and the minimum value. Then the skewness is the skewness measures the asymmetry of the ECG waveform distribution. And lastly, the kurtosis, it measures the peakedness or the flatness. As I said before, high kurtosis leads to sharp peaks, and the low kurtosis indicates flatter waveforms. The extracted features are later used as inputs for the machine learning models. Now I will let you continue with my friend Amna.
Assalamu alaikum. I am Amne الشمايله. I will continue discussion for this project. And this slide, we used two machine learning model. The first is the logistic regression model because it is what we sent in our discussion, and the second is the support vector machine using the RPF kernel. This is mainly applied for the purpose of the comparison. And the logistic regression, this enables the analysis to explain which variable impact the decision. And in this slide, this is the code of the model training, and show the training of the logistic regression model. We have trained the model, checked the accuracy, produced the cohesion matrix, and graphed the ROC curve. And the ROC is the receiver operating characteristics curve, is a tool, and it is a tool that assists in assessing the ability of the given model to distinguish between healthy sample and samples that belong of especially classes myocardial. And I will explain this code quickly. This line we use to import the logistic regression model and evaluation matrix and ROC function. And this line we create a logistic regression model and train him, and in this line we make prediction and test data and calculate and print evaluation matrix. And in this line from code, we get the probability of the positive classes and calculate false and true positive ROC curve and the area under the curve. And in last lines, we used it to draw the ROC curve and evaluate the model performance. And in this slide, the slide result. And the logistic recursion model achieved an accuracy of 62.5%, while the support vector machine achieved 53.1%. And the most important, the rate of the recall of myocardial infarction was 75%, and in a medical diagnosis, recall is critical because missing a myocardial infarction case is much more dangerous than a false alarm. And in this slide show the ways in which outliers were defined statically. We used both Z-score and IQR method in defining outlier from the extracted features, and there were outlier in terms of thickness and peak-to-peak value, and this reflect the natural variability of the ECG signal across different patients. And this slide we show the code of the outlier detection. This code show ways in which outlier were defined statically, and finding the outlier help us in understanding the distribution feature. And I will explain this code quickly. This line we use to import the library that we need, and this line we use to list the feature used in dataset, and this line we used to organize the feature into a table and add the classes label, and this line we used to calculate the Z-score and discover the outlier in the data, and this line we used to IQR method also to discover the outlier in the data, and these two lines are used to show the number of the outlier were found, and the last line we used to display the first row of the data table. And in this slide, the model interpretation, one explanation of the data from the logistic recursion coefficient analysis, the thickness was discovered by the variable was discovered to be the K variable, and thickness is measure of the asymmetry of waveform, and the peak-to-peak amplitude was also significant as myocardial injury may decrease the ECG amplitude. And this slide error analysis, we examined the false positive as well as false negative, and some myocardial infarction ECGs appear normal, causing error of the classification, and false negative are even more serious since they represent missed heart attack cases. And in this slide, ROC curve, receiver operating characteristics curve, show an area show that the area under the curve is 0.66, and this suggests good separation between the normal and the myocardial infarction classes. And even if not perfect, this model classified correctly better than random classification. And in last slide, what we learned from this project, interpretable machine learning model with a sample feature are also capable of achieving a good result, and ECG variability and noise can greatly impact performance and generation, and myocardial interfection causes characteristic change in the ECG wave pattern, and in conclusion, our approach display a clinical potential. However, further work can be done by employing more feature and larger dataset.